In this video, we're going to look at a solution to quiz number 4. Um, let's see, here is the quiz problem. There are two problems to it. The first problem is to consider the function e to the negative x squared minus y squared, and to compute the tangent plane, and then to do the curve on the surface in a given direction, 2, 3. So let's take a look at this function f of xy. This is part 1. F of xy is equal to e to the negative x squared minus y squared. And I'll just consider part of the solution here. We'll just look at the point 1, 1. And the first part, A, let's find the tangent plane to this function at the point 1, 1. Okay, the second part, B, to find the curve on the surface, curve r of t on the function z is equal to f of xy in the direction v is equal to 2, 3. So to find the curve on the surface in this direction and its tangent line. And then the third part is to plot all these curves together. Okay, so I'll do the two parts by hand, and then I'll let you see the solutions that are in Google Drive for the student solutions that I've done a very good job on for the plots. Okay, so here's our function. Let's finish this problem number 1 first. Okay, so for part A is pretty straightforward. You need to find the equation of the tangent plane. That's the linearization, L of xy. It's simply the function evaluated at the point that you're interested in. In this case, we're interested in 1, 1. I'm going to compute the partial derivative of f in the x direction, evaluated at 1, 1. I'm going to multiply by x minus 1. I'm going to look at the partial derivative of f with respect to y at the point 1, 1, and I'm going to evaluate it at multiply it by y minus 1. Okay, so there's what you need to do. It's pretty straightforward to compute this computation, so just make sure you double check f sub x, the partial derivative of f with respect to x, okay, is the partial derivative with respect to x of the function e to the negative x squared minus y squared, which is simply e to the minus x squared minus y squared multiplied by the derivative of the inside function, which is negative x squared minus y squared, and then this piece is negative 2x. Okay, so similarly, you should find f sub y is equal to e to the minus x squared minus y squared multiplied by negative 2y. Okay, pretty straightforward to compute these partials at the point 1, 1, for example. You will get e to the negative 1 minus 1 multiplied by negative 1 minus 1. Okay, and that turns out to be negative 2 over e squared, or negative 2 e to the negative 2. And the partial derivative f with respect to y turns out to be the same thing, negative 2 e to the negative 2. Okay. And then we also need the function evaluated at 1, 1. And that's simply e to the negative 2, or 1 over e squared. So your tangent plane is pretty straightforward to write down. L of xy is 1 over e squared minus 2 over e squared, x minus 1, minus 2 over e squared, y minus 1. And there is your tangent plane, the explicit form, meaning that L of xy, you've written it down as a function of x's and y's, and those x's and y's are to the first power, x and y to the first power. Okay, if you wanted to write down the implicit form would be negative f sub x evaluated at 1, 1 times x minus 1 minus the partial derivative of f with respect to y evaluated at 1, 1, y minus 1 plus 1 times z minus the function evaluated at 1, 1. And that would be set equal to 0. This is the implicit form. So the implicit form of the plane would be 2 over e squared, x minus 1, plus 2 over e squared, y minus 1, plus 1 multiplied by z minus 1 over e squared equals 0. So you have two choices for the tangent plane, and it's pretty straightforward to plot those two functions. Okay, so that handles part A. That handles part A, and that was a reboot from a previous quiz. Part B is to find the tangent line and curve to this surface. Z is equal to e to the negative x squared minus y squared. At the point 1, 1 in the given direction 2, 3. Okay. So the straightforward answers are here. The curve on the surface, r of t. This would be the curve on the surface. It would be 1 plus 2t, 1 plus 3 times t. And then you would get e to the negative 1 plus 2t squared minus 1 plus 3t squared. That's your curve on your surface. If you were to look at the tangent line to the curve in the direction v, you would get 1 plus 2t, 1 plus 3t, and then you would get the function evaluated at 1, 1 plus some number multiplied by t. And the number that goes here is the gradient of the function evaluated at 1, 1. And then you would dot product that with your direction vector v. And this vector v is 2, 3. Okay. And I think we decided that our gradient was, I think we can see it here, negative 2 over e squared, negative 2 over e squared, and negative 2 over e squared. So the number that should go there would be negative 4 over e squared minus 6 over e squared, which is otherwise known as minus 10 e to the negative 2. So that would be the number that would go there, negative 10 e to the negative 2. Okay. That is one possibility, or you could write the following. You could write 1 plus 2 over the square root of 13t, using the fact that you're trying to use the unit vector of the direction v. This would be 2 over square root of 13, 3 over square root of 13. Okay. And in which case you would have the function evaluated at 1, 1, which would be 1 over e squared. And then you would get minus 10 e to the negative 2 over the square root of 13. And then you would have to multiply that by t. Oh, sorry. Okay? So you could have this answer or this answer. You should not combine those two. If you put 2 and 3 here, don't put, so the incorrect answer would put 1 plus 2 over square root of 13t, 1 plus 3 over square root of 13t. And the incorrect answer would put 1 over e squared plus something times t. It would be incorrect here to put the gradient of the function dotted with v. That would be incorrect. If you put 1 plus 2t, 1 plus 3t, 1 over e squared, it would be incorrect to put in this blank the gradient of f dotted with u, okay, where u is the unit vector of v. Okay, so these two are correct. These two are incorrect because you're mixing unit vector with the gradient dotted with a non-unit vector. Here you have your direction v is not a unit vector, but you've dotted the gradient with a unit vector, so there's a mismatch there. Okay, So there are your answers to the tangent to this problem, finding the tangent plane and finding the curve on the surface in that given direction. Okay. If you'd like to see a plot here, here's what we're looking at. We're looking at our function. Here is the point 1, 2. Here, I think we're looking at, here. This is the x-axis. Here's our point, our point 1, 2. Here's our direction 2, 3. The black dotted line is your curve r of t, and this line here is the tangent line to that curve at that point. And you can see that if you zoomed in, it does actually look like it's the tangent line. Okay? So it does actually look tangent. Okay? And I think you can see over here, on the side, here are the computations. Okay, I compute the gradient. There's your gradient. Evaluated at the point 1, 1. Our point x naught, y naught is 1, 1. There's your gradient at that point. Here's your direction vector 2, 3. Do the gradient dotted with that direction vector, and you get minus 10 over e squared. Your curve on your surface, here's your curve on your surface. Okay, and here is your tangent line. Okay. So that concludes, well, this solution if we're showing it by hand. That's your solution by hand. Let's go over here and show quickly how to just really kind of snappily compute in Mathematica the answer to this quiz. I would first make my function f of xy equal to the exponential negative x squared minus y squared. Okay. So there's the function that we're concerned about. Okay. We're interested in the point 1, 1 and its tangent plane, so you simply have to make the tangent plane L of xy. It's a function of x and y. It should be the function evaluated at 1, 1. Okay. Plus, I see. Let me first make my derivative. Okay, let me do this quickly. This should be the gradient of f. Okay. The gradient of f, it's a function of x and y. Okay. So I'll take the derivative of my function. And this is a quick way to get the gradient. You just say xy. Okay. And let's get rid of this for a second so you can see my derivative. Okay. There's your gradient. So if you take the derivative of your function and say take the derivative with respect to x and y, here is your gradient. Okay. Now take your gradient of your function evaluated at 1, 1, and there is your gradient evaluated at 1, 1, which is what we saw before. Okay. Now let's compute our tangent plane. Make it a function of x and y. It would be the function evaluated at 1, 1, plus my gradient of my function evaluated at 1, 1, and then I need to compute a dot product of that with the vector x minus 1, y minus 1. And that's the really simple way to write your tangent plane formula. Okay? And there is your tangent plane, which you could easily create a plot of with plot 3D. And plot this, say, from, say, -3 to 3, and, well, I'll let you show the details here to build up the right plot. Okay, but there is a plane, and if you plot your function on top of that, plot your function f of xy, you can see the function, and you can see its tangent plane at this point. Okay, probably zooming in near the point 1, 1. Maybe we could look at 0 to 2, and let's zoom in closer to 2. That would say maybe 1 to 3. Okay. Can't remember. Okay, but that's how you could get the tangent plane and its function on the same plot together. Okay. All right, so that would be a quick way to get the tangent plane and the function together. So I'll leave you to look at the solutions for that to complete the problem. Okay. There's a part 2 to this problem. There's a part 2 to the quiz, and let's take a look at that now. Question number 2. Okay. And question number 2 is to consider this function, x squared plus 4y squared at the point 2, 1. And this point, find the equation of the contour curve through that point. Okay, so why don't we do that first? Our function was, what was it? X squared plus 4y squared. So we have a function g of xy is x squared plus 4y squared. Now we know that's some kind of surface. Okay, they gave us a point x naught, y naught. Okay, and x naught, y naught was, what was it, 2, 1? Yep, 2, 1. Okay. And we want to find some sort of level curve on here. So we need to compute the level curve. Okay. Which level curve is that on? If you look at the point g of 2, 1, that would be 2 squared plus 4 times 1 squared. That would be 8. So if you look at this curve, 8 is equal to x squared plus 4y squared. There is your z is equal to 8 level curve of the function g of xy. Okay. Now this can be plotted in the xy plane, and it is some sort of ellipse. Okay, this is a formula for an ellipse. Now what you were supposed to show in this problem, what were we supposed to show? Find the equation of the contour curve through this point. Okay, so that would be 2a right there. Okay, you need a contour curve. The result we're trying to show is that the gradient is always perpendicular to this contour curve. So let's first parameterize the curve from A. And what we mean by that is we need to take the curve x squared plus 4y squared, and we need to write this down as a curve x of t, y of t. Okay. And it is a curve that if you substitute in for x here and you take this y and substitute in for y, you better get 8. So can you think of an x and a y that if you plug it in will give you 8? The answer is square root of 8 cosine t. Now this is just one possible answer. One possible answer is x of t is equal to square root of 8 cosine of t. Y of t. If this was a hint for x, can you figure out what y has to be? It would be the square root of 8 sine of t, but then you have to divide by 2. Because when you take x of t and you square it, you get 8 cosine squared of t. When you take y of t and square it, you will get 8 over 4 sine squared of t. And therefore, when you multiply y by 4, 4y squared is 8 sine squared of t. And because x squared plus 4y squared is 8 cosine squared of t and 8 sine squared of t, and because of the trig identity cosine squared plus sine squared, you in fact get 8. So here is our curve. Okay, so we have completed part B, which is to parameterize this curve and show that its direction vector of this contour curve is always perpendicular to the gradient. So if you would continue here, B, what we are trying to show is that the gradient okay, gradient of g is always perpendicular, okay, the gradient of g is always perpendicular to the level curve, okay. So what I mean by this, if you compute the gradient, okay, the gradient is 2x, 8y. The gradient of your function g is 2x, 8y. Okay. Now we know that this, if you plot the gradient, it's a vector field at any point that you pick. What we were trying to show is we need the gradient only evaluated at those points along the curve. So I'm only trying to show that the gradient is perpendicular to the level curve when the gradient is at those points on the level curve. So what you need to do is compute the gradient of f evaluated at your curve. Okay, this is otherwise known as the gradient along the level curve. And the simple answer to that is that it is 2 multiplied by 8 cosine of t. So wherever I saw the x, I put in what my value of x was along that curve. And then I will get 8 square root of 8 over 2 sine of t. Okay, so there's the gradient along the curve. That would be this arrow at any point along the curve. Okay. We now need to show that it's perpendicular to the level curve, which means that I need to compute the direction vector. Here's the direction vector of your level curve. Compute the derivative of it. Well, the derivative of the curve is just going to be the square root of 8. Derivative of cosine is negative sine. So that would be negative square root of 8 sine of t. And then the derivative of the y value is going to be square root of 8 over 2 derivative of sine is cosine. Okay. Now we should be able to check that the gradient, when you look at the gradient, those arrows only at the points on the curve, and you dot product that with the derivative of your curve, which means just the little direction vectors here, okay, those should come out to be 0 when I take the dot product. So that would give me 2 square root of 8 cosine of t, 4 square root of 8 sine of t. So here is the gradient. And dot product it with minus square root of 8 sine of t, and 8 square root of 8 over 2 cosine of t. So let's see what happens here. I get 2 with a negative square root of 8 times square root of 8 is 8. And then I'll get cosine of t sine of t. And then I need to add that to let's see, what am I looking at here? Gradient. 4 square root of 8. Okay, what is this a 2? Yes, this is not a 12, that's a 2. Right, r prime, yes, it's square root of 8 over 2. So when I take gradient dotted with this, the 2, yes, here we are, 4, sorry, 4, I'll get 2 square root of 8, square root of 8 times square root of 8, and then I'll get a sine of t, cosine of t. Okay. Square root of 8 times square root of 8 is 8, and they have opposing signs, and they have a sine and a cosine, so these are the same value, and you get 0, which implies that the gradient is perpendicular to the level curve. Okay. And this is for all values of t. Okay. And you were supposed to create a plot which maybe showed that, which showed some contours and maybe showed your gradient. I'll leave you to look at the Mathematica solutions for that problem. So in this video.